Good afternoon, everyone. My name is Dave Entwistle, Chairman of the IMechE Aerospace Northwest Committee. Today, we are bringing you what promises to be a very informative overview of COMSOL's modelling simulation software. Your speaker today is Robbie Balcom, Technical Director at COMSOL. He graduated from University of Strathclyde in 2007 with a Man-Eng in Aeromechanical Engineering, and then carried out his PhD in the area of numerical modelling of rolling contact fatigue at Imperial College London. The webinar will consist of around 50 minutes of lecture, followed by Q&A coordinated by Turai Rulan, also from the committee. If you have any questions, please pop them in the chat box on your screen, and hopefully we'll manage to touch all the questions. So without further ado, I'll hand you over to Robbie.
Thanks, Dave.
Thanks, Robbie.
And thanks for joining me for this webinar this afternoon entitled Improving Designs with Multiphysics Simulations and Optimization. So the first thing I would like to do today is to start by putting the term multiphysics into context. So what I might describe as the traditional approach to numerical modeling involves partitioning the full spectrum of physics into kind of smaller application areas. So typically we might partition the full spectrum of physics into electromagnetism, into structural mechanics, acoustics, fluid flow, heat transfer, and so on. And we might focus on simulating within one of these application areas in isolation. When we talk about multiphysics, what we tend to mean is actually looking at a scenario where rather than focusing on just one of these branches of physics, whether it's structural mechanics or heat transfer or fluid flow, what we're actually doing is we're looking at a scenario where we're combining more than one branch of physics together in a single model, in a single modeling environment. So we're looking at how these different physical effects interact with each other, and we're simulating them and their kind of interactions. Now, the reason that we choose to kind of adopt this multiphysics approach to simulation is that very often, real systems that we might want to simulate don't comfortably fit into a kind of pure structural or pure thermal sort of category. And to be able to kind of realistically simulate a system, very often we need to be able to capture the interaction between these different physical phenomena. So the intention here by bringing together different branches of physics into a single multiphysics simulation is really to be able to kind of improve the resolution and improve the accuracy of the simulations. Now, today, during the presentation, I'm going to talk about modeling in different branches of physics, such as structural mechanics, fluid flow, and heat transfer. But what I'm also going to talk about is bringing these together and capturing their coupling and their interaction. And that's kind of where I'm going to start. And then what I'm going to do is I'm going to move on to a kind of another sort of facet of the computational modeling, and that is optimization. When we're engaging in computational modeling, what we're generally trying to do is we're trying to optimize a design, and we're trying to use computational models to inform us along that process of optimizing a design. I guess a sort of traditional modeling workflow might involve us working through that process iteratively, using our own engineering knowledge of the particular design or device that we're simulating, where we would use our understanding of the problem to make design changes, rerun a simulation, and hope for a better outcome. But what I'm going to talk about is actually running numerical or mathematical optimization, where what we're actually doing in this instance is we're actually handing over control to an algorithm to perform this design refinement process for us. So in this kind of workflow, we're no longer the ones making the design changes, but it's down to us to be able to quantify what would be the optimal design, or what would make one design better than another design. So in terms of kind of COMSOL multiphysics, so COMSOL Multiphysics is a modeling platform that allows you to kind of set up and run multiphysics simulations, bringing together these different branches of physics. And we also have something that we call the application builder as well, which I'll talk a little bit more about in a second. So in terms of COMSOL Multiphysics as a software platform, it is a platform that kind of is composed of three different facets. We have what we call the model builder, which is what you can use to kind of configure and set up your multiphysics simulations. We then have something that we call the application builder that allows you to convert your multiphysics simulations into what we would describe as a modeling app, i.e. something that a non-modeling specialist can use. And then we have something that we call the model manager. And this is a sort of file storage system that allows you to efficiently store the data that's associated with your simulations and your computational models. So first of all, to introduce the model builder, this is the kind of COMSOL modeling environment, and it's based around this model builder that you can see here on this slide. And this is essentially a sort of logical workflow that you would typically follow to set up your simulation within a graphical user interface. The simulations don't have to be multiphysics, so you can model mechanical problems, you can model heat transfer problems, but of course you can also model the thermomechanical problems. So you can model multiphysics or single physics simulations within this model builder if you want to. But it provides a sort of logical modeling workflow that you can use to kind of set up and run your simulations. You have a graphics window here that displays geometry and displays results. Now, typically we might expect someone who is familiar with computational modeling and is somewhat of a modeling specialist to work within the model builder and build up a simulation. And then what we can do is we can actually convert that simulation into what we would call a simulation app. So this slide here gives you an illustration of what a simulation app might look like. And this is something that can be developed using the tools within this model builder environment. And essentially what you're doing here is you're designing something that, rather than allowing someone to build up a simulation from scratch, allows them to take an existing simulation, modify some of the operating conditions, or, for example, the geometric dimensions, and rerun the simulation. So this is something that that we could use to reach a wider audience. It could be used within a large organization as a way of sharing simulations with colleagues, or if you're working as a consultant, it could be something that you could use as a deliverable to a client. And then finally, we have this model manager, which is essentially a data management system that allows you to more efficiently store the data associated with your simulations and your models, where you can do things like version control. And if you're saving versions of models, what you're saving in terms of data is only what you have added to the model since you previously saved it, rather than saving a complete a version of the model every single time. So you don't have 10 versions of the same model that are slightly different. So before I kind of move on to talking about the physics or physics in more detail, I just kind of wanted to quickly throw up this slide here, which kind of mentions the democratization of simulation. And democratization is really a kind of buzzword that's being used a lot in the kind of simulation industry. And these different kind of facets of the software are intended in some ways to try and kind of meet this challenge of democratization. So the idea here is that we want to be able to reach a wider audience with computational modeling. We want to be able to allow people who don't have an advanced degree in engineering or science, or have experience even with computational modeling, to still be able to run simulations and to be able to leverage the results and to use the results of running simulations. So we have the kind of COMSOL Multiphysics software that allows you to kind of build up those computational models, and then these can be converted into simulation apps that can then be used to reach a much wider audience. These simulation apps can be deployed in different ways, one of which is that they can be compiled. So you can compile an app as a kind of standalone executable that can be launched from anywhere without access even to a COMSOL license. And the idea here is that this could almost be used in the way that spreadsheets were used in the past, where someone put together a spreadsheet that had a few numbers that could be changed, and then you could compute some results. And this app idea is intended to work on a similar principle, so that we can reach a wider audience, and a wider audience can benefit from computational modeling. So what I have here on this slide is I have a user story from one of our users, St. Jude's Medical. Now, this is a story where they developed something called a left ventricular assist device. And for those of you who aren't familiar with what this does, is the purpose of this device is intended to either replace or assist with the functioning of the heart. And it's typically for patients which have suffered heart failure. Now, the reason I've chosen this particular example is because it demonstrates a good scenario where multiphysics has been used in the development of a product. So in this particular example, the design that St. Jude's Medical came up with for the operation of this LVAD is essentially based on using a magnetic field to drive a rotor. Essentially, the device itself will operate like a pump. So the way that the heart would pump the blood around the body, this is intended to replicate that. Now, the mechanism that they used was based on using a magnetic rotor. So we have here a magnetic field, which is going to generate a torque, which is going to drive a rotor, which is very similar to the way that an electrical motor will work. So we have some electromagnetism here that we need to consider. The torque is then going to mechanically drive the rotor. So we also need to consider mechanics. But we also need to analyze the flow of blood that this pump is going to generate as well. So in terms of simulating this system, we need to consider combining electromagnetism with mechanics and also with CFD. Now, we also, because this is a device which is going to be inserted into the body, we need to make sure that it doesn't interfere with the kind of biological functioning of the body as well. So as well as analyzing the device itself and how the device will operate, we also need to do some thermal management analysis as well to make sure that the power that's associated with the magnetic field that's driving the rotor isn't generating too much heat inside the human body, that it will interfere with the kind of biological functioning. So there is also a thermal element involved with simulating this system as well. So in terms of developing this product, they have simulated this in a holistic way by looking at combining electromagnetic modeling with mechanical modeling, with CFD modeling, and also doing some separate heat transfer modeling as well to understand the thermal effects. And that's actually what you can see here on this slide here. This is the heat that's being generated by the power supply. So in terms of kind of talking about the physics modeling functionality within kind of COMSOL, I've kind of decided to start on kind of home turf here. So I've kind of started out by covering the structural mechanics modeling functionality. Now within sort of structural mechanics, you can look at modeling with a variety of different element types. So you can in COMSOL use solid elements, shell elements, beam elements. You can use a variety of different study types. So you can do static analysis, you can do dynamic analysis. The dynamic analysis can be done in the time domain or in the frequency domain. There are also some specialist analysis types available as well. So you can look at things like response spectrum or random vibration analysis. So if you were looking at mounting something on the fuselage of an aircraft, you might want to understand how it would respond to random vibrations due to turbulence. Or if you were looking at a medical implant in the knee or something like that, again, this might be a scenario where random vibration would become of interest. And I've also highlighted a few other modeling features within mechanics which may be of interest. So you can do contact modeling. You can model bolts and bolt pre-stress. We have functionality for modeling cracks. This can be both pre-existing cracks that exist in the geometry or cracks which will actually initiate and propagate through mesh elements. And you can also set up models which combine different element types. So you can set up hybrid models which are composed of different elements, such as this model here, where we're looking at combining shell elements with beam elements. In terms of material models, we have linear material models and also some multiphysics material types, such as piezoelectric materials and magnetostrictive materials, so smart materials. And we also have nonlinear material models available as well. And these are kind of split into two categories. So you've got your structural nonlinear material models, such as hyperelastic, elastoplastic, and creep. And you've also got your geomechanics nonlinear materials, which would be your kind of more naturally occurring materials, things like soils, rocks, and materials which would typically be used in geophysics type modeling. Moving on to talking about heat transfer. Within COMSOL, you can model heat transfer by the three main mechanisms. So you can model heat transfer by conduction, you can model heat transfer by convection, and you can model heat transfer by radiation. When it comes to looking at convection modeling, you can look at both forced and natural convection. So you can look at something which is driving the flow, like a fan, so a forced convection, or you can actually just look at naturally circulating air, for example, which is what you can see in the animation here. And when looking at convection, it will often, require us to model not only the heat transfer, but also the fluid flow as well. And you can easily set up that multiphysics coupling, where the flow could be either laminar or turbulent. For looking at radiation, we can consider radiation from a variety of different kind of perspectives or different levels of sophistication, I guess. You can look at an object simply losing heat through radiation, or surface to ambient radiation, as we would call it. So losing heat to the ambient environment through radiation. You can look at also surface to surface radiation. So this would be a scenario where objects that are in the line of sight of each other are able to transmit and absorb heat through radiation to each other. And you can also look at something that we call radiation in participating media. So this is where we're looking at a semi-transparent material. So in the case of a semi-transparent material, we have the heat being transmitted through the material, but as it's being transmitted through, some of that heat is being absorbed. So if we were looking at glass, for example, looking at glazing in a building, this would be a scenario where this could be useful. Now, when it comes to kind of multiphysics and structural mechanics, the most common multiphysics coupling is probably looking at thermal structure interaction. So where we're combining heat transfer with mechanics, and we're looking at how the material will expand as it's being heated. And of course, this expansion can then lead us to thermal stress. And this is something that you can simulate in COMSOL Multiphysics. You can also extend this to consider a scenario where the heat source is actually an electrical heat source. So what we could actually look at would be electrical heating and how that electrical heating will lead to thermal expansion. And this could be interesting if we're looking at things like circuits, or if you're looking at MEMS devices. Some MEMS devices actually rely on this expansion for the purposes of actuation. You can also look at something called thermoelasticity. So where we're looking at mechanical vibration, we may have some damping within the material, and we may want to actually calculate the generation of heat due to the losses due to damping in the material. So the energy that's lost to damping, we can convert to a heat source, and we can actually calculate how much heat that will generate. Now, moving on to talking about fluid flow, we can analyze a variety of different categories of fluid flow problems. So first of all, here I have porous flow. And this allows us to look at the flow through a pore structure, which is actually what you can see in the image. But when we work with porous flow, rather than actually creating a pore scale structure with all of the detail, what we can actually do is we can approximate this by using some averaged properties across the domain, such as the porosity and the permeability. So we can look at modeling of porous flow. We can look at modeling of free flows. So this is flow in a non-porous material, essentially. And this can be laminar or turbulent. For looking at modeling of turbulent flows, you can model turbulence using the Reynolds averaged method, or RANS, or you can model it using LES. And in our upcoming release, we will also be adding DES turbulence models as well. You can also look at multi-phase systems. So this is looking at a fluid flow problem where we're dealing with more than one fluid. So we're looking at a scenario where we have two fluids that don't mix. So we're looking at immiscible fluids, and we will track a sort of fluid-fluid interface. And you can also model polymer flow, or essentially fluid flow where we're dealing with a complex rheology. It's not limited only to polymers, but to fluids where we're dealing essentially with either non-Newtonian fluids or viscoelastic fluids. So complex shear rate viscosity relationships, nonlinear shear rate viscosity relationships. And when it comes to kind of the looking at multiphysics within fluid flow, what you can see here on the left-hand side is fluid structure interaction, where we're looking at combining fluid flow with mechanics. And what you can see here in this animation is a scenario where we have a fluid which is deforming a structure. And that's one way that we can model fluid structure interaction. So the flow deforms the structure. The alternative way would be actually to look at the mechanical deformation driving the flow, which might be something that we would look at if we were modeling a pump, for example. You will also notice here that we're looking at a mesh which is moving. When working with fluid structure interaction, if we're dealing with large deformations, it's important for us to actually be able to model the flow around the deformed structure as opposed to the undeformed structure. And the way that we deal with that is by actually deforming the mesh so that we can actually update the shape of the structure during the simulation and model the deformed shape as opposed to the initial shape. As I've mentioned already, we can look at coupling of heat transfer with fluid flow to model the effects of convection. And we can also look at coupling what we call thin film flow with structural mechanics. So thin film flow is where we're dealing with very thin layers of fluid. And this is typically used in lubrication type simulations. So we solve what's called a fluid shell, which is based on the Reynolds equation. And this can be used in lubrication type modeling, so hydrodynamic lubrication or elastohydrodynamic lubrication. And it can also be used to analyze things like damping, air damping, and things like MEMS devices. Now, moving on to the sort of next sort of branch of physics that I wanted to talk about, I guess for a kind of mechanical engineering audience, the modeling of electrochemistry might not be something that's perhaps as relevant or as familiar, but you can actually set up electrochemical models within COMSOL Multiphysics, and we can analyze the batteries using a variety of different levels of fidelity in terms of setting up the models. So on the left-hand side, what you can see here is a very high fidelity battery model where we're looking at analyzing the electrochemistry on the full pore structure geometry. So we have this very high fidelity model of the full pore geometry. So this is giving us a very accurate simulation, but is quite expensive to compute. We can then look at a somewhat simpler scenario here, where rather than modeling the full pore structure, we approximate the pore structure and we homogenize the pore structure using effective or average properties across the domain. But we're still solving the problem using a three-dimensional CAD type geometry. We can then simplify this even further to where we're actually only modeling a battery using a 0D model or as a circuit model, where in this scenario, we're neglecting any variations in space. We're only calculating some what we would call lumped properties, such as the voltage or the current, or crucially, the power that we will have associated with our batteries. Now, you can model batteries using these different methods in COMSOL, and where I guess it ties into perhaps more mechanical engineering is if we're looking at perhaps thermal management of batteries, we can utilize, for example, these lower resolution models of the battery and the electrochemistry to provide a heat source that we can then couple to a three-dimensional CAD heat transfer model to calculate the temperature that's being generated within a battery pack. Or if we're using the more high fidelity methods of modeling the batteries, then we can look into things like the mechanical degradation of the batteries. So we can actually couple the electrochemistry with mechanical modeling. Now, within a battery, if we have the buildup of lithium ion particles within the crystal structure, what we can end up with is a scenario where the buildup is essentially causing this to expand, which will cause stress buildup and strain buildup within these particles. And if we're cycling this process repeatedly, then what we will end up with is essentially a sort of classical mechanical fatigue problem, where we were getting this cyclic stress build up within our battery material, which will eventually lead to failure within our battery. And we could also consider effects like hydrogen embrittlement and the effect that that will have on the mechanical performance of a battery. So the last sort of branch of physics that I wanted to kind of run through is the electromagnetic branch. And you can set up and run electromagnetic models within COMSOL. And these can either be set up to model at the high end of the electromagnetic frequency spectrum or at the low end of the electromagnetic spectrum. So if we're dealing with high frequency electromagnetic problems, then we would typically model this as a wave problem. And this allows us to look at things like, say, microwaves and antennas. So we might be looking at something like a medical device where we're using microwaves to heat a cancerous tumor, where we're looking at something like ablation, where we might couple high-frequency electromagnetics with heat transfer. At the lower end of the frequency spectrum, where we might be dealing with frequencies that we get, for example, from the mains voltage, or we might even be dealing with DC cases where the frequency is 0. We can analyze electric currents, and we can also analyze magnetic fields. And we can couple the electromagnetics to mechanics. When we're dealing with very small length scales, such as those in MEMS devices, the effect of charge becomes proportionally more important. And at very low length scales, we can actually find ourselves in a scenario where the forces associated with charge are enough to deform a mechanical structure. And in fact, this effect is leveraged in a lot of MEMS devices to actually actuate switches. So this is something that we can model. And we can also model magnetomechanics as well. So this is looking now at the effect of a magnetic field as opposed to an electrostatic field, and coupling the effects of a magnetic field with a structure. So we're essentially looking at how the Lorentz force due to the magnetic field will cause a structure to deform. And this could be used to model things like solenoids, plungers, or transducers, like you can see here in the image on the slide. So in terms of kind of structural mechanics and multiphysics, the slide here kind of gives you an overview of some of the common multiphysics couplings that we see when working with mechanics. This isn't an exhaustive list, but it gives you an overview. So we have thermal expansion, we have fluid structure interaction, we have the piezoelectric effect, we have acoustic structure interaction. So this is looking at the sound that's generated by mechanical vibrations. This could be looking at machinery noise or looking at loudspeakers, for example. We have things like electromechanics and magnetomechanics, and one that I haven't mentioned yet, which is hygroscopic swelling. So this is looking at moisture content and how that will cause a structure to expand. Now, this gives me a good opportunity to remind everyone that you can actually ask questions. We will have a Q&A session at the end. So if you have any questions on maybe multiphysics couplings that I haven't covered that you would be interested to know more about, then please just pop a question in and we can address those questions at the end. So I want to move on now to talking about optimization. So what I have on this slide here is I have what you might describe, first of all, as a kind of conventional modeling workflow. So what we have here on the left-hand side is we have some inputs that we need to define. So we need to provide some input parameters for our kind of computational model. And these will typically include dimensions for our geometry, material properties, and operating conditions. So we provide those inputs. We have our kind of computational model here at the center, and this is something that will be computed, using, a commercial software, for example, such as COMSOL Multiphysics. So we run our simulation, and then we will get some numbers out of our simulation. Now, as I said at the beginning of the presentation, in a kind of traditional or conventional modeling workflow, what we would typically do as engineers is we would analyze the outputs from the simulation, and using our engineering knowledge, we would then adjust the inputs to the simulation. We might change the geometry, we might change the material, then we would rerun the simulation, and we would hope for a better outcome. And we would essentially repeat this process and refine the design until we feel that we've reached the kind of optimal design. When we work in an optimization workflow, this process is slightly different. And I'm first of all just going to introduce some nomenclature that we use when talking about optimization. So the inputs to the simulation that we can modify in order to improve the design, i.e. the inputs that we will allow the optimization solver to modify, we would call the control variables. So those are the variables that our optimization solver has the freedom to modify and to update. The simulation that we solve, we would typically refer to as the forward problem. So this computation here is the forward problem. Then we have our objective function. Now, the objective function is something that we use to quantify how good a design is, and something that we can use to compare one design with another design. And when working with optimization, we either want to maximize or minimize the objective function. And this is something that must evaluate to a number, because the computer needs to be able to compare by using a numerical value. So a common optimization process that we might run would be to minimize the amount of material that we have in our design. In that case, our objective function would be our mass. And what we would want to do is we would want to minimize our mass. So we have our objective, and then we will also have some constraints. We need to limit the size of the design envelope for the optimization solver. Now, constraints can be limits that we impose on the control variables, or constraints can actually be constraints that we impose on the physics problem. So we might say that the displacement must be lower than a certain value for the design to be permitted. And in some cases, it's very important that we have these constraints, because if I go back to the example that I was talking about, where we're optimizing for the minimum mass, if we have no constraint on this problem, the optimal solution is actually to remove all the material, because that's the minimum mass. So we need constraints to ensure that we will get a physical solution as the output of our optimization study. So the way that this kind of workflow is different is that now, as engineers, what we need to do is we need to define the objective and we need to define the constraints. The process of actually updating the design is now done by this optimization algorithm for us. So essentially, we're automating this process of refining the design to a certain extent. And what it will also do is often the optimization algorithm may come up with a design that we would never have thought of. So we may end up with something that's more novel than we would have considered based on our own understanding. Now, when it comes to looking at optimization problems in COMSOL Multiphysics, some of the different optimization tasks that you can run are included on this slide. So you can look at design optimization, where we're essentially working with a geometry and we want to optimize the geometry. Or you can work with parameter estimation. This is essentially inverse modeling. With parameter estimation, we know the solution that we want, but we don't know the inputs required in order to obtain that solution. This could be used to find material properties, for example. So using the battery example again, we may easily be able to charge and discharge a battery, but it might be very difficult for us to understand what the internal chemistry within the battery is. So we can actually reverse engineer it. In terms of design optimization, we can do different types of design optimization. So we can use shape optimization, which allows us to change the shape of surfaces. Topology optimization, which will essentially work out the best distribution of material. So essentially what we would do here is provide a block, and the optimization solver will carve out the shape from a block of material. Or we have parameter optimization, which will essentially take a dimensioned CAD geometry, and it will work out the optimal values of the CAD dimensions within the geometry. In terms of defining an objective function, the software supports user-defined objectives. And this is true when you're working both with a gradient-based optimization solver and a gradient-free optimization solver. COMSOL Multiphysics actually supports both. But you can work with your own user-defined objective functions. So you can define an objective to be whatever you want it to be. So this brings me to the demo part of the webinar. So what I'm going to do here is I'm going to run through how to run an optimization study on a multiphysics problem. So the multiphysics problem that I want to go through is called a plate heat exchanger. And what we want to do in a heat exchanger is we want to exchange as much heat from a region where we have a high temperature liquid to a region where we have a low temperature liquid. So essentially what we're doing here is we want to heat up the cold channel as much as possible. Now, the way that we can quantify the amount that our cold channel has been heated is actually by evaluating the power. So we want to know how much power we are transferring here from the the high temperature channel to the low temperature channel, where we have one on top of the other, and it's split by a surface. So the objective is to maximize the heat exchanged. The control variables in this case are going to be associated with changing the shape of the plate, which separates the high and low temperature channels. So we're going to allow the optimization solver to essentially come up with what is the most efficient shape of this surface that splits the high temperature channel from the low temperature channel. And in terms of the physics involved with modeling this problem, we have a combination of heat transfer with fluid flow. So in terms of the kind of forward problem, the physics problem to start with, we have a high temperature channel on the bottom, and we have a low temperature channel on the top. Now, I'm just going to consider one section of this heat exchanger just to simplify the problem. Now, I understand that I don't actually have an image of a real heat exchanger on my slide, so I thought I would just very quickly here jump across to Wikipedia so that you can get an idea of what a real one of these might look like, so you can see something here. So we have lots of these in sequence, but I'm just going to be looking at a single plate in this example. So in terms of the setup of the physics problem, we have a cold fluid inlet, we have a hot fluid inlet, we have a cold fluid outlet, and we have a hot fluid outlet. So we have an inlet in terms of the flow, and we also need to provide the temperature of the fluid as it flows through those inlets. The flow is going to be a pressure-driven flow. So we will have a higher pressure at the inlet, lower pressure at the outlet in order to drive the flow. Now, because this is intended to simulate a stack of these plates, I will use a periodic condition on the top and bottom, and this is intended to give the effect of this being a repeated stack of these plates in reality, whereas in the model, I'm only looking at just simulating a single plate. Okay, so what I'm going to do now is I'm going to come out of the slides, and I'm going to switch across to COMSOL Multiphysics. So the first thing I'm going to do here is I'm going to pull some notes in front of me with some numbers. Then I'm just going to select Model Wizard. I'm going to set up this model in 3 dimensions. And then I need to select what physics I want to use here to simulate this problem. So this is going to be a heat transfer problem, but it's going to be a combination of heat transfer and fluid flow. So I'm going to use what's called conjugate heat transfer, and I'm going to assume that the flow is laminar here. I could also model a turbulent flow, but I'm going to base this simulation on an assumption that the flow will remain laminar. So I'm going to add that to my model. The next thing that I'm going to do here is I'm going to choose a study type. So I could run this as either a stationary study or as a time-dependent study. If I wanted to pulse the flow, I could run it as a time-dependent study, but I'm just going to assume that we have a continuous flow. So I'm going to run it as a stationary study. When running an optimization problem, it's also worthwhile making the forward problem as quick to compute as possible, because you might have to compute the forward problem 20 or 30 times. So you want the forward problem to be something that you can compute quickly so that you can reduce the total time of the optimization study. So I'm going to work with a stationary study. Now, once I've made those selections, it will take me into the kind of model builder building environment here within the software. Okay, so I'm now into the model builder. Now, the first thing that I'm going to do here, just to quicken the process of building the model, is I'm going to load in some parameters. So I have my parameters here. So I'm just loading in some parameters in a text file. And these will include some dimensions for my geometry and also the operating conditions. So the pressure and also the 2 temperature conditions. Okay, the next thing that I'm going to do is I'm also going to copy in my geometry rather than building it. So in the geometry node here, I'm going to choose the insert sequence. You can also build the geometry, or you could import a CAD geometry. But I'm going to skip that, and I'm just going to select my COMSOL file and insert the geometry sequence. So I'm going to build that. Okay. So I have my geometry. The next thing that I'm going to do is I'm going to assign the material to the geometry. And what you should begin to see now is a kind of pattern emerge. And I'm just kind of working my way down node by node here in the model builder. And that's essentially the COMSOL workflow. So here in the materials node, what I'm going to do is I'm going to add my material. Now, I failed to mention in the slides, but the material that I'm going to use here is water. So I'm just going to add this from a library of materials. You can also define your own, but as I'm working with water, it's available as a predefined material. So we have water assigned to the entire geometry. Okay, now you'll notice here I have heat transfer and I have laminar flow. So essentially what I need to do is to set up those two separate physics problems. I need to set up the inputs for calculating the flow, and I also need to set up the inputs for calculating the heat transfer. You'll also notice that there's a multiphysics node here, and this actually takes care of the coupling. This kind of takes care of the coupling for me, where the flow is automatically being coupled to the heat transfer. So let me start by setting up the flow. So in terms of defining the flow, I want to add some inlet conditions and I want to add some outlet conditions. So first of all, I'm going to add an inlet, and I'm going to add the inlet here, and I'm just selecting the boundaries of the geometry that I want to form the inlet just by clicking on them. So I have the 4 boundaries selected here, and that's going to be my inlet. And I'm going to define the inlet using a pressure, and I've defined this as a parameter, so it's 5 millipascals. So I have my first inlet. Now I'm going to reuse this selection, so I'm actually going to name it. I'm going to call this inlet 1. Okay, so I'm going to add a second inlet now in the top part of the geometry, and that's going to be over on the side here. So I've got my second inlet, and again, I'm going to use the same inlet condition here. I'm going to define it using a pressure, and I'm going to call this outlet 2. The reason I'm naming this selection is so that I can reuse it later on. So I've added my inlets. I'm now going to add my outlets. So for the bottom channel, the outlet is going to be here, and the outlet condition I'm going to define just as a 0 pressure. And then I'm going to add a second outlet condition here on the top channel. Okay, so I have my inlet condition on the bottom channel, my inlet condition on the top, my outlet on the bottom, and my outlet on the top. The last thing that I'm going to add here is I'm going to add a partitioning boundary just to split this channel in half. So I'm going to add here an interior wall, and I'm just going to select this boundary here. This is to split this into 2 channels, essentially. Okay, so I've configured my flow part of the model. I'm going to move on now to setting up the heat transfer part of the model. So temperature 1 here is high temperature, temperature 2 is low temperature. So temperature 1, which is the high temperature part, will be the bottom. The lower temperature part will be the top. So in terms of setting up my heat transfer part of the model, the first thing I'm going to do is I'm going to define that all of my domains are fluid as opposed to solid, because in heat transfer, we can actually define them as either. So both are fluid. I'm going to add a temperature boundary condition, and I'm going to set this to T1, which is the high temperature, and I'm just going to select the inlet 1. So that is why I named those selections, so that I could select them now. I'm going to add the second temperature, which is the lower value, and I'm going to select inlet 2. I've called this outlet hot. Oh, I called it outlet 2. Okay, bear with me a second. I've been doing this too quickly. I'm just going to change this to inlet 2. Okay, so if I go back here, I now should have inlet 2. Okay, so I've added the temperature conditions to define what temperature the fluid enters, but I also need to add an outlet condition for the flow as well. So I have my outlet 1, which I have named. Okay, so I have my outlet 1, and then I also will add my outlet 2 to the model as well. Okay, so I will add my outlet 2. Okay, so I've added all of my boundary conditions. The last thing I want to add here is I just want to make this a periodic problem for the heat transfer. So in terms of setting up the sort of forward problem, the physics problem, that's everything defined. I've configured my heat transfer model. I've set up my fluid flow. I have my coupling. The last thing that I want to do here before I compute is to mesh. Now, you can work with a physics-controlled mesh, which would generate a CFD mesh, but I'm actually just going to use a user-controlled controlled mesh where I'm actually just going to create a swept mesh. So I'm going to use a structured mesh here, something like this, okay? So what I would do now is I would hit compute, but I've actually computed this already. So I'm just going to jump across here to the model where I've actually calculated already the forward problem. It computes quite quickly, but I'm conscious of my time and I want to make the most of the time that I have remaining. So here what I have is I have the solution to my forward problem. Now at the moment, the plate which separates these two channels is flat. That's the initial condition that I've used here. And what you can see here on these arrows is the streamlines of how the fluid is flowing in the two channels. The blue lines indicate the cold channel, the red lines indicate the hot channel. Now, what I've done here is I've actually added some additional variables that allow me to actually evaluate the amount of power that's being transferred. So the way that I've done this is I've essentially calculated the power associated with the fluid as it exits the cold channel and the power associated with the fluid as it enters. If I subtract one from the other, then I can actually calculate the accumulated power in the colder channel whilst the fluid is in the heat exchanger. And this is what I want to maximize, the accumulated power in the cold channel. So that's what I've defined here as these additional variables. And I can actually output this power. So I've got about 9 watts of heat exchange. And this power is actually what I want to maximize using optimization. So what I'm going to do here in this model is I'm now going to add the optimization to it. I've computed the forward problem. I've converged it. Now what I'm going to do is I'm going to add the optimization. So in the component 1 node here, I'm going to add shape optimization. I'm going to run this as a shape optimization problem because what I'm going to do is I'm going to change the shape of this surface here in order to increase the amount of power that's being exchanged in terms of the heat exchange. So I'm going to add shape optimization, okay? And I'm just going to assign that to my geometry. Now you'll notice that deformed geometry has also appeared here, and that's the way that we compute shape optimization. Rather than rebuilding and remeshing the geometry, what we're actually doing is deforming the shape of the boundary. And we deform this using a polynomial function. But all of that is formulated for us behind the scenes. All I need to do here is I need to select the boundary of the geometry that I want to modify using shape optimization. What I also need to define here is a maximum amount that the boundary can be deformed. And this is going to depend on the height of the channel here, because we can't deform the boundary more than the height of the channel, because then we would have a scenario where our walls would start to intersect. So we will limit the amount that this can either move up or down. And that's what this maximum value is doing. The next thing that I'm going to do here is I'm going to go to the study node. And in the study node, I'm going to add a shape optimization node here. Now, within the settings, I can choose between different optimization solvers. These are all what are called gradient-based methods. So I'm going to use IPOpt. Now, my objective function here is actually going to be this power that I have here as a variable. And this describes the amount of power that's being added to the cool fluid channel. So that is what I'm going to use as the objective for my optimization. So I'm going to put this in as my objective function. And rather than minimizing this, I actually want to maximize this power. So in terms of the type of study that I'm going to run, I'm going to maximize it. And I'm going to use initial solution-based objective scaling. So this will scale the value of the objective function using the initial value when you run the problem. Okay, so I hit compute on that, and then I come over here to my computed solution. So this takes about 40 minutes to compute, and it runs almost 20 different iterations of the problem. If I go here, I can look at the difference in temperature. So if I plot the temperature map for the flat plate, we can see this fairly large area of lower temperature. If I increase the solution number here to my final optimized solution, we can see that we have a much higher region of high temperature, which suggests we have more heat being exchanged. We can actually look at the objective here to quantify exactly the amount of heat that's being exchanged. So with the flat plate, we had about 9.4 watts, but with our optimized solution, we're up to 12.2 watts. So that's an increase of around 30% in the performance here with respect to this objective that we have got by running this optimization study. Now, what I'm going to do here is I'm going to actually just animate what the optimization solver does. So what we will see here is how it changes the shape iteratively and works towards the optimal solution. So we should see that the first solution is a flat plate, but we work towards this plate here, which actually has these dimples here. Now, what we can see here, if I go to the streamline plot, is that by changing the shape of the surface, we're increasing the length of these streamlines. We're actually obstructing the flow from going directly from inlet to outlet, and we're forcing it to remain in the channel for a longer period of time because our streamlines are longer. And because of this longer residence time, we're getting a better heat exchange between the cold and the hot channel within our heat exchanger. Okay, so what I'd like to do now is I'd like to just hand back to our moderator, who is going to ask the questions that you've been submitting during the presentation.
Right. Hope you can hear me.
Yes.
Good afternoon, all. First of all, thank you, Robbie, for that brilliant presentation. I got about 8 or 9 questions, so I'll group them together. First of all, the 2 questions which I think are interlinked is there's one from Tatiana, and basically it's asking, can we model solid state phase change like for material processing such as quenching? And a similar question, I think, from Hadi Farouk. Does the software package allow ability to simulate collision and fracture mechanics of hammer, mill, etc.? I thought they were both involved.
Sure. So dealing with the first part of the question, the solid state phase transformation. So what I have here in front of me is actually the different modules that you can that we provide essentially. So we have a metal processing module, which is intended for modeling solid state phase transformations. So looking at the decomposition, for example, of martensite into other phases as the material is cooling. And this could be used for looking at, modeling metal processes like quenching and so on. In terms of fracture mechanics, yes, you can model fracture mechanics. We have the phase field method implemented that allows you to look at modeling of cracks and modeling of crack propagation. What I would add, though, is if you're using this phase field method for propagation, there's a certain amount of smearing that is done across the crack and the crack tip because we're not resolving it nodally. Essentially, it's got the freedom to propagate through mesh elements. Now, this provides flexibility because it allows you to look at branching, for example, and it allows you to look at initiation, but we will sacrifice some accuracy in terms of stress intensity factors at things like crack tips. There is also a crack feature that you can use that will give you an accurate stress intensity factor calculation, but that is mesh-based, so is limited by meshing. So you can't look at propagation using that method.
Thank you very much. There's another, you're desperately short of time, so I'll just squeeze in 2 more if possible.
Yep.
One of them is, it involves a question from Andrew Manning. In your CFD simulation, are you able to create a simulation app and then edit the mesh, but keep the boundary conditions, or does it work by keeping the same mesh and varying the boundary condition?
So you can change the mesh. What essentially you would need to do is to define a parameterized mesh. And then what you can do is you can allow the app user access to change the parameters, and then that would propagate down through the model and update the mesh. So yes, you can change the mesh and retain the same boundary conditions if you wanted to. So you would, for example, be able to do a mesh refinement analysis in an app, but that would require some pre-preparation of the model before you make it an app to allow for that sort of functionality.
Thank you very much. And I think just one last question from Editor Schroeder. Can we calculate all iterations in parallel mode?
In optimization, it will depend what type of optimization problem optimization solver you're running. Some optimization solvers are history dependent, i.e., they use the information about the previous iterations in order to inform them where to move forward. So these are the sort of gradient-based or derivative methods. These can't be computed in parallel just purely because of how the algorithm is formulated. If you're working with gradient-free methods, then you can compute in parallel and then use the information about the parallel computations to update. Also, if you're doing Monte Carlo analysis, then you can do a large amount of parallelization. But in that case, you're essentially mapping out the entire sort of parameter space. So only some of the optimization solvers can be computed in parallel.
Thank you very much. At this point, I'd like to take the opportunity to thank Dr. Robbie Balcom for an absolutely brilliant presentation on COMSOL, the Multiphysics, its capabilities, and especially the optimization solver. That was what caught my imagination most. It was also illustrated with a very nice worked example. I'd also, at this point, would very much like to thank Emma Pateman, Matt Nichols, Dave Entwistle, Rebecca Donald-Lopez, and all attendees for making this a very educational and informative session, and enjoyable too, with plenty of beautiful high-resolution color graphics. It's very much appreciated. Thank you once again, and bye for now.